rendering showing that the modular robot's performing some tasks like load carrying and setting up some truss structure. And the one in the bottom, that one is a very phenomenal work by Japan Advanced Institute of Science and Technology. It's called MTran robot, modular transformer. So you can see it can actually perform reconfiguration. So if you look at just one module, this is the CAD rendering for our ModRed robot, the one you can see here. So this is just a CAD rendering before fabrication, and you can see that how each of the modules work. Like this module has 4 degrees of freedom. You can see the arrows showing the degrees of freedom, and it has, in the 2 sides, it has 2 docking mechanisms. So modular robots, they have some degrees of freedom for some amount of autonomy that they might have, and they have some docking mechanisms so that they can attach with other modules and then form larger teams. Some other characteristics of modular robots is they are mostly symmetric. So even if it topples down, or they can actually easily get back to their original position or use that topple condition already. This is again MTran robot. And MTran robot again. Modular robots are really good in reconfiguring, so that's why they are good candidates for traversing over different types of obstacles and experiencing different types of environments. So this illustration shows that case. Now here's the overview of my dissertation. So this is, of course, a picture in Mars. Of course, not a real one, it's a virtual picture. And it shows 1 to 8 is the chapters that I have in the dissertation. So we start with introduction and literature survey. And then you can see that there is a condition like some robotic lander soft landed here, and then the robots, they came out of the system, and they're trying to survive in this environment. So they want to sustain in Mars terrain. And they have some positive and negative obstacles, and they have to perform tasks, they have to perform locomotion, and so on. So in chapter 2, we introduce our robot, ModRed, especially its kinematics and some level of electronics. ModRed 2, which was designed specifically for rough terrain traversal purposes. And then chapter 4 is self-healing of a modular robotic system using a docking mechanism that we developed. We're coming back to this later. And then the locomotion gates using ModRed and ModRed 2, both type of robots. So you need to perform locomotion on these rough terrains in such a way so that the robots can survive there and perform tasks. Then chapter 6 is avoiding obstacles while carrying a load. And chapter 7 is when you have no way to avoid the obstacle. So there's a theory proposed there telling like how you can actually get over the obstacle. And finally, the conclusions and future directions. So we begin with some of the previous works. The first one is by Straub, and it's about, both of them are actually about wheeled rovers, and those are some really good contributions in sustainable robotics and of course in planetary terrains. So the second one is cooperative robots, where they perform cooperation while one robot is hanging from a cliff and supporting the robots. And this is by Pirjanian and Schenker, and I can probably see Dr. Faber's name there too. Yeah. So there was actually, I think it was there like in the mechatronics lab, and they took it out now. But they had the artificial Mars cliff there with the 3 of the robots cooperating each And then getting more specifically towards modular robots or modular self-reconfigurable robots, we have a very good contribution by Dr. Mark Yim, which is called Polybot, which is a 1 degree of freedom robot. So each of the robot modules are 1 degree of freedom, and when they connect with each other, they form teams like this. And Superbot, Dr. Wei-Min Chen's work, 3 degree of freedom robot, and both of them are actually made for traversing over rough terrains and obstacles, as in the planetary surfaces. The later one, I know that it was funded by NASA. Partially. So let's get back to Modred. How did we design our robot and how it performs? So Modred has 4 degrees of freedom with one novel prismatic degree of freedom. So using these degrees of freedom, the robot is very flexible, and it's kind of high compared to the other existing modular robots, the degrees of freedom available. And the robot had 2 docking mechanisms in 2 ends. So these are the initially developed docking mechanisms for Modred robot. And for actuators, we use stepper and gear motors. So getting to the forward kinematics for this robot, we can get the workspaces, approximations. So using only one module, we can get like a half toroid shaped workspace. So that is how far the robot can reach. And using only 2 modules, we can get near spherical configuration or workspace for it, which is actually a very desirable characteristics for any manipulator or robot. Now, if we use this forward kinematics, we can find out the Jacobian matrix, which relates the function of the forward kinematics with the joint variables of this robot. So it has 4 joints, so it relates those joint variables here. And finding determinant out of this and equating to 0, then performing numerical analysis, we get this graph where you can see that these are the positions where the robot is, it actually encounters singularity. So singularity is a thing where the robots are not acting stable. So we have some of these configurations where the robots act kind of erratically. We don't want to go there. So compared to this half toroid shape, you'll see that here it's not a lot of space that is actually acting erratically. And these 2 pictures, they show the advantage of having the linear degree of freedom, which is explained in the first picture where docking or undocking becomes really easy using this degree of freedom. Also some adjustments for the length for the module. And the table that shows that we have 4 degrees of freedom with our robot. Now if you freeze 1 degree of freedom, it's 3 degrees of freedom right now, right? So here you can see like there are 4 configurations available using 3 degrees of freedom and so on. So out of these configurations, like some of them are existing modular robots. So if we freeze 1 or 2 degrees of freedom, the remaining ones, they can act or they can achieve the configurations which some other modular robots already developed. We can also get from that. Now this is the control architecture for the Modred robot. We have in the middle the blue one, that one is the computer, and mostly we have the inputs and outputs that were connected to this. For the outputs, we have the motors and solenoids that ran these motors, robots' different degrees of freedom and the docking mechanisms. And we had sensors like infrared sensors, compass sensors, and tilt sensors to understand like what is the orientation of the robot and how far the obstacle is from the robot. So those are some of the characteristics. Now, moving from moderate 1, the first version, as you see here, we have designed moderate 2, which is the second or improved version. And there is a big difference. Like most of the parts will be designed, fabricated using plastic to make it lightweight, but we have the 2 degrees of freedom in front and back, and as well as we have a couple more docking mechanisms actually in the 2 sides. So that will increase the ability for getting more configurations. You'll see in the next chapter after this. So moderate 2 was specifically designed for rough terrain traversal, and in actuators, in MIT there was a work on series elastic actuators where it said that rigidity is not always desirable. You can have some flexibility in the design so that it can take shocks in a better way, pretty much like the shock absorbers in the cars. So we added some springs, a couple of linear springs with the motors, so that in the rough terrain, whenever the robot is moving on the rough terrain, there is uncertain conditions. And when the motor actually gets some kind of shock, then those springs, they can absorb